Transformation temperatures. These are the temperatures where materials, and specifically metals, start to experience a change in their lattice structures. We have the lower transformation temperature and the upper transformation temperature. Let's talk about each one of these. The lower transformation temperature. This is where the bodied centered cubic structure starts to change to a face-centered. This is where the temperature, ferrite, starts to change to austenite. The lower transformation temperature for all iron and steel is around 1,330 degrees Fahrenheit or 720 degrees centigrade. The upper transformation temperature. This is where bodied center cubic structure has completely changed to face-centered. At this temperature, no ferrite exists. The material is 100% austenite. If the metal is allowed to cool back down to room temperature, it changes back to 100% ferrite. If the metal is quenched to cool rapidly, it changes to martensite, bodied center tetragonal, instead of ferrite. The upper transformation temperature varies for each metal. It may be as low as 1,330 degrees or as high as 2,000 degrees Fahrenheit. And here's your austenitic chart. And it shows you as the temperature starts to rise, how the austenite and the ferrite percentages change as it gets hotter. And then once it gets above the upper transformation temperature, it is 100% austenite. And then if it slowly cools, it cools right back down to 100% ferrite. If we fast quench it over here, it turns into 100% martensite. Crystal growth. If a material is cooled slowly, the grain size is larger. If the material is quenched or cooled rapidly, the colonies or dendrites are smaller, resulting in a smaller grain size. Grain size greatly affects the strength, hardness, brittleness, and ductility. Metals that have a large grain size are easier to tear, break, or fracture. Metals with a smaller grain size have a higher resistance to fracture. The smaller the grain size, the greater the strength. The larger the grain size, the lesser the strength. The smaller the grain size, the harder, stronger, but more brittle the material. It's the metallurgist's job to find the proper metal properties for each particular application. And here's a crystal growth pictorial. Here's your molten, so it's far above the transformation temperature, molten iron. As it starts to cool, you see your first unit cells start to form, and then the branches develop as the iron cools. They start forming into geometric shapes. And then it continues to cool. Several colonies, which are called dendrites, form. And as the solidification nears completion, the boundaries start to contact each other. And after it's totally cooled off, the iron has many. Grain size versus cooling time. Well, slow cooling, large grain. Quick cooling, small grain. So the large grain size is weak, ductile, easy to tear, fracture, or break. Small grain size, strong, brittle, resists fracture. Cracks are stopped by a series of small grains. And here's another pictorial. Slow cooling, large colonies, large grain size. Fast cooling, many colonies, small grain size. Figure 717 in your book. The effective grain size. And again, large grain size creates a weak and ductile, easy to tear. Small grain, strong, brittle, resists fracture, and the cracks are stopped by a series of small grains. Do you want strength and hardness? Make your grain small. If you need ductility, make your grain size large. Here's an example in your book about paper is more difficult to tear when it's made up of many small pieces glued together. And it tries to follow where it's connected, which would be similar to what's in metal, the grain sizes where they contact each other. Another example is like splitting wood. Straight grain wood is easy to split until you hit a knot, where the grain changes the direction. Lots of knots, lots of stops. Grain boundaries stop cracks. Just remember that.